Hello friends, this video will be very important for you. In this video, we'll discuss a couple of concepts. We'll start with the cache replacement algorithm. In cache replacement, we'll discuss about LRU, least recently used algorithm in this lecture. Immediately after cache replacement, we'll discuss about a very important topic called virtual memory. Immediately after virtual memory, we'll discuss some of the important topics or important discussion on secondary storage. So in secondary storage, we'll discuss about magnetic hard disk. So without wasting your time, let's start the video. Before we discuss the actual algorithms, let us discuss what is replacement algorithms all about and why we need these algorithms. Now consider a situation where your cache memory is very small. Maybe it can contain only 4 information at a time. And your cache is already full. It is containing some information from main memory. Of course, you cannot store each and everything from your main memory. Only some important information you can keep, right? So your cache is full, containing all the information, all 4 information. Now suddenly your processor is asking for some new element. Now your cache is full. Now where to store? Suppose you want to insert a new element to your cache, how you will decide where I shall insert this new element because your cache is full. That means from your cache memory, some information has to be moved out so that new element can take the place. Now, which element you will kick out or move out, you cannot randomly just decide which element you will just eliminate from the cache, right? To decide which element you want to eliminate so that new information can occupy the space is nothing but replacement algorithms. We have many replacement algorithms, but in COA we have one most important algorithms to be discussed, which is LRU. I hope you understood what is replacement, right? Replacement is nothing but just replacing your old information with some new information when your cache is full. Now replacement algorithm is necessary so that we can decide accurately which element I shall eliminate from the cache. Randomly I cannot eliminate anyone. Now to decide that, we have several algorithms. One of the most important algorithm is LRU, least recently used. Now from the name itself you can at least guess what I will do with this algorithm. Least recently used means the oldest one. Least recent means the oldest one. From my cache, I will see which data is the oldest data, means which data is occupying the space from a long time. So in using LRU, I will eliminate that oldest data with the new data, whatever you need to insert newly. You understood that? So we'll discuss this algorithm with the help of one example. It will be more clear to you. Suppose I have a small cache of only four slots. I have only 4 slots in my cache. It's a small cache and I want to insert some data. My CPU is asking for some data like this. So how to deal with that? First of all, say your CPU is asking for A and initially your cache is empty. Nothing is there. Forget about this here. Nothing is there in your cache. Your CPU is requesting for A. So A is not there. It's a cache miss. Now what we will do? Your cache will request the data from main memory that give me this particular data. What is that particular data? A. Now A can be placed anywhere because my cache is empty initially. So I am placing my A here. Fine. Next your CPU is asking for B. No, B is not there in my cache. So again it's a miss. But I can store my B anywhere because I have available space. So I'm keeping my B here. Next, your CPU is asking for C. Cache miss, but I can store C in my cache for the future purpose here because I have available space. Here I am asking for A again. My CPU is asking for A again. So A is already there. So it's a hit. Now here forget about this A. When I had A, B, C, if I ask you which one is the oldest one, A was the oldest one, B was the second oldest, and C is the third oldest, right? But here in this stage again your CPU is looking for A and A is a hit. Now this A is no longer the oldest one. You understand? This is the recently used one now. So don't be confused. So A is the recently used one, B is the most oldest, and C is the second oldest now. You understood that, right? Next I want to insert D. Yes, D I can insert here because I have available space. Next, what I want? I want to insert E. Now you have to decide, because your cache is full. Now there is a problem. You want to insert E and your cache is full. Where to insert this E? Now we are using LRU, least recently used. So in least recently used, which one I will eliminate? The oldest one. Now which one is the oldest one? It's not A, because A is recently used here. As I told you, B is the oldest one. So I will replace this B with E. You understood that? Again, after some time, I am requesting, your CPU is requesting for A. Now again, A is the recently used one. Fine, A is there, it's a heat and it's using most recently. It's not the oldest one. Again, I am requesting for D. D is also is there. So D is also not the oldest one now, recently used one. Now I want to use C. Yes, C is also there. It's a heat. C is the most recently one. Now which one is the oldest one? A is also I have used recently. D also I used recently. C also I used recently. E is the oldest one now, right? So if you want to insert F now or some other element, I have to eliminate this E. E is the oldest one. Fine. I hope you understood. So this F is taking place here. So A, F, C, D. Now it's a small example and it's very easy to determine which one is the oldest one. But I will suggest you to use some numbering. In exam you may get a very complex example, not a very simple example like this. And that time it will be very confusing to decide which one is the oldest one. For that I will suggest you to use some numbering. What kind of numbering? This kind of numbering you use. Means if I have only 4 slots, then I will use 00, 01, 10, 11. Fine. And 00 is the recently used one. 11 is the oldest one. This is how we will decide. So like this, if you do the numbering, no matter how many elements you are inserting, by seeing the number only you will decide which one you have to eliminate or which one you have to replace. Fine. See here what I am doing. Initially I have to insert A. So A I am inserting and I am putting the number as 00 because this is the most recently one. Next I am inserting B. Now B is 00. B is the most recently one. A is the second recent one. Fine. So this one is 00. This one is 01. Next I want to insert C. Now C is the recent one. So 00. This 00 will become 01 and 01 become 10. Next again you want to access A. Now A is the recently one. So A is 00. This 00 will become 01. 01 will become 10. Next you want to insert D. So D will be the recent one, 00. Rest all you just increase by 1, whatever you have. Wherever you had 00, here you had 00, so it will become 01. You had 10 here, it will become 11. You have 01 here, it will become 10. Fine. Next you have E. So now where you will insert E? See here. So from here, from these numbers, which one is the oldest one? 11 I said. Where is 11? Here. So you just eliminate B and insert E here. Now E will become the recent one, so 00. And rest all is just increased by 1. This one will become 01, this one will become 10, and this C will become 11. Fine. So after that, say you want to insert after E, A. So A again will become 00. This one 01, 10, 11. C is already 11, right? Next you want to access D. Now D will become 00. This will become 01, 10, 11. Next C. Now C where is C? This one. Which was before 11, now it will become 00 because C is the recently used one. Now you want to insert or you want to get F. F is not there. Where to insert F? This place because E is having 11, the oldest one. This is how it works. Fine. So that's all about LRU, least recently used. But again, in exam, if they mention about some mapping techniques also, like set associative, and direct mapping, this LRU techniques you have to be very careful. If they say direct mapping, we know for direct mapping there is a fixed place where I can store the element. If it is the first memory block, then I have to insert to the first cache block only, no matter how many empty space you have. So for direct mapping, your LRU won't work perfectly, right? Because it does not matter which one is the oldest one. It matters about the position. I want the first position, I will get there only, no matter which it is recently used or the oldest one. So in direct mapping, LRU does not work. Associative mapping, this is the example of associative mapping, right? I can store anywhere. In set associative mapping, so it's 50-50, means first of all, the first memory block will go to the first set of cache. Among first set, now you have to check which one is the oldest one, but it should be there inside set number 1 only. Fine. So you have to be careful in exam if they mention about the mapping techniques also. So that's all about LRU or page replacement technique. So the most important discussion about cache memory we have almost done. Now we'll discuss a little bit about virtual memory. Now if I ask you, do you know about virtual memory or any idea about virtual memory? Yes. Let me take a very small example for this. Suppose you want to play a game, maybe Free Fire you want to play, and the game size is say 6 GB. The size of the game is 6 GB. You want to play in your mobile, but unfortunately your mobile RAM is only 4 GB or 3 GB. Now we know whenever you want to execute any program, it should be executed through your RAM or main memory. But your Free Fire is having 6 GB, requirement is 6 GB for Free Fire, but your RAM is having only 2 GB or 3 GB. In that case, how you will deal with this situation? You cannot deny to play the game, right? Your mobile should not reply like you cannot play this game. So what is the solution? The solution is your RAM, your main memory will borrow some memory from your secondary storage. You have enough secondary storage, right? Maybe 1 TB, 500 GB, whatever. So in that case, what your main memory will do is it will borrow some part or some memory from secondary storage, not all. For our example, where I had only 4 GB of main memory, I need 2 more GB to store the game information, right? Because my game size is 6 GB. So 2 GB will be occupied or will be borrowed from your secondary storage. Now you have 6 GB space. So your processor will think that you have enough space to play the game and you can start the game. Fine. See this example. So 4 GB is this is one more example actually. 4 GB is the program requirement and you have only 2 GB of RAM. What your RAM will do or main memory will do? It will borrow 2 GB from secondary storage. Now you have 2 GB plus 2 GB, 4 GB. Now all this 4 GB can be occupied these spaces. Fine. How it will be occupied? See, I have A, B. So how it deals with? So whenever we play the game Free Fire, it's not that in a second or in a click I finish all the things, all the games, whole games. It's not possible, right? It takes time. We have several stages, maybe several levels. We'll finish one level, then second level, third level, like that we finish the game, right? It's not at once we finish everything. So the concept is we'll divide the process or the game or the program, whatever you want to run, into several portion or several parts like that. For example, I have 4 GB process or game. So I'll divide it into 4 parts, A, B, C, D. So each part will be containing 1 GB, 1 GB, 1 GB, 1 GB, 4 GB. So now what I will do is, I have 2 GB main memory. So this 1 GB will be occupied 1 GB from here. This 1 GB will be occupied here. Next 2 GB I will be storing in my secondary storage. Why I am doing that? Because we know I can borrow memory from secondary storage. That's fine, I borrowed. But whenever you execute the program, I cannot execute in secondary storage, right? I have to execute through main memory only. Now you will say how it is possible, because you are occupying from secondary storage and you are saying I cannot execute from secondary storage. It's very confusing. Let me make it very clear. So what I will do is, initially you have started playing the game, say stage 1, which is A. Fine. And A is stored where? In your RAM or main memory. So you can easily execute this. There is no question about that because it's already there in RAM. Problem is with C and D, right? So you are playing A, and after some time all the information or all the requirement from A is over, or your level or stage of game is over. First level is done, you have completed A. Now what you will do next? You will go for the second level or second stage B. Yes, B is also there in the RAM. So you start playing, you are playing B. Meantime, what I can do is, this A is already over, right? This stage you have already done. So what I can do is, this C from secondary storage I can copy here, so that it will be stored in main memory only. So once your B or second level is done, you will go for third level C. Now where is C? C will be there in place of A, because A you have already played before and this C is occupying this space. Now you will get everything in main memory only, not from secondary storage. You have to move from secondary storage to main memory. Fine. So this is how your virtual memory works. Before that, you have to remember some things. Whenever you partition your process or game or program, whatever, into several parts, we call it as pages. So this is page 0, page 1, page 2, page 3. You may have some more pages also. It depends on the system or application. Now this page 0, page 1, page 2, page 3, I have 4 pages. I won't say 4 levels or 4 stages. In virtual memory terms, we will call it as pages. Fine. Now whenever you want to insert these pages to somewhere in main memory, then again obviously this slot size and this size should be exactly same, otherwise you cannot copy this page here to here, right? So here we call it as page and here we call it as frame. What is frame? Frame is the address where I am storing the pages from the processor. So frame 0 will contain page 0, frame 1 will contain page 1, and so on. You understood what is pages and what is frames? Frames in the main memory, pages in the process or the game or the programs. And this page size and frame size is exactly same. So this is how your virtual memory works. So you have a block diagram how it works. Your processor, now one more thing I forgot to explain here. So whenever your processor, this is the game or process, right? Whenever your processor will generate some address to execute any one of these stage or pages, it will generate the address in terms of 4 GB, not in terms of 2 GB. Because your processor will assume that you have enough memory, that's why you accepted to execute this program. Your processor never care about how much RAM you have. When you have accepted, your processor will assume that you have enough memory. So your processor will generate some address of 6 GB. Sorry, 4 GB, not 2 GB. Although you have only 2 GB RAM, it will generate the address of 4 GB. Now it's the responsibility of your RAM to translate this 6 GB address to 2 GB, because you have actually 2 GB. It's kind of you lied to your processor that I have enough space, I can execute the program, but actually you don't have. So when your processor is asking a large memory address, this is your responsibility to convert it to something smaller addresses in 2 GB, because it should be there in 2 GB whenever you are executing. I hope you are understanding it, right? So for that, the address which your processor is generating is known as virtual address, because this is not the actual address. Actual address should be there in main, should be for the main memory only, not including the secondary storage. So the address which your processor will generate will be the virtual address. Then there should be someone to translate this virtual address to your physical address or the actual address, right? So who will do that? MMU, a small hardware component in your computer, memory management unit. This is a hardware. So whenever your processor is generating some virtual address, your memory management unit will translate it to physical address, and it will ask for cache first, whether whatever your processor is asking is there in cache or not. If it is there in cache, then obviously it will send it to processor. If not, then what I will do? I will go for main memory. Fine. So if it is there in main memory, I'll send it to cache, from cache to main memory. If it is not there in main memory, then I'll go for the secondary storage. Fine. From secondary storage, I can get the data. So this is how it works, actually virtual memory works. Now among all these stages or steps, the most important step I will say is to translate from virtual address to physical address. How to deal with that? Suppose your processor generated some address. So this address will be initially divided into 2 parts. Whenever your processor asks for any virtual address, it will be divided into 2 parts. One part is virtual page number and one part is offset. Offset will be maybe your block number or your byte number, anything. So virtual page number, say your processor is asking for page 0 offset, anything, it can forget about offset, page 0, your processor is asking for page 0. Now where is this page 0? From where I will get? Because this page 0 can be anywhere, right? It can be anywhere. So how I will get where is my page 0, whether in frame 0 or frame 1? There may be multiple frames. I have taken a very small example, but in reality you will have n number of frames, n number of pages. So who will tell me that this page 0 is there in frame 1 or frame 2 or frame n? How will I know that? For that we have a page table. Fine, we have a page table in main memory. This page table has the information that your page 0 is located in frame number 1 or 2 or 3, wherever. You understood that? So whenever your processor is generating a virtual page number, if I get this page table, then I will easily know the frame number. What is frame number? Frame number is the actual address, right? Where the data is present in main memory. This is frame. So if I know the frame number, I know the actual address. So this page table will help you to determining the actual address or the physical address or the frame number. So here I'll have page number, frame number. So whatever page number your processor is requesting, I'll go to this table and I'll find the frame number. Now it seems like very easy process. If I have a page table, it's very easy process, right? Now the problem is, I'm talking about only one game or one program you are running. At the same time, you can run n number of programs, maybe 3-4 games you are playing or movies you are playing, so many things you are running, and everyone is using some virtual addresses, some virtual memories. Now there is a problem. How will I get the correct page table? If you are running 2 programs or 3 programs at the same time, that means there should be 3 page tables, right? For game 1, you have a page table. For movie you are playing, you have a page table. Separate table will be there for separate programs. Because at a time you can play multiple things, right? So in your main memory, don't think you have only one single page table. You have n number of page tables, depends on how many programs or processes you are running at the same time. Now the problem is, if I get this page table, problem is solved. To get this page table is a problem now, because you have many page tables in the main memory. Which page table you will go for, right? Page table for game, page table for movie, page table for MP3, so many things. Now which one is the correct page table for you? For that, I have a special register called page table base register that knows where you have to go. Which is the correct page table for you. Means when you get the virtual page number, it won't directly go to the page table, but it will go through page table base register. This base register has the information about all the page tables, so it will redirect you where you have to go. Table number 1, 2, 3, 4, 5. So once you get the correct page table, the rest of the things are very easy, because you have the page number and frame numbers. You will get the frames. You understood that? So this is how it works. Now once this process is completed, once you got this thing, then we have the same concept of cache here also. Once you have done with the first step, we'll store this to some cache memory. And we won't say exactly as cache memory, but we call it as translation look aside buffer, TLB. It works like your cache only. Once the first step is done, you store it into cache, so that next time if you want the same page number, then no need to go through all the steps or all the stages, right? So this is how it works. So once it is there in your TLB, translation look aside buffer, or similar with cache, next time whenever your processor is generating some virtual address, it will go through this cache or TLB. If it is present, then we'll call it's a heaped. If it is a hit, then directly you will get the page number and offset, because it's already there. If no, then we will follow this step. Fine. If it's a hit, then directly we will get. If it's a miss, then we will go for all these steps again. Fine. Now we won't say it as a cache miss or TLB miss here. We have a standard term for this. We call it as page fault. Fine. Page fault means it's a miss. Now when page fault occurs, what you have to do? You have to take it from the memory. Fine. And again, if your TLB is already full, then what you have to do? You have to replace some pages, and you have to replace some old pages with the newest one. For that also, again, we can use the same concept called LRU. Fine. Least recently used one. So this is how your virtual memory works. So I have discussed only the most important things about virtual memory. So now I'll discuss about a little bit of secondary storages, or I'll say magnetic hard disk. In secondary storage, I have many options: secondary magnetic hard disk, floppy disk, CD disk. Many options are there. The most important one is magnetic hard disk. So what is magnetic hard disk and how it works? So we are done with cache memory, we are done with virtual memory. Now we'll be completing secondary storage, specifically magnetic hard disk. So how it looks like and how it works. So although this diagram is it's not a good diagram I have drawn, but I'll try to explain this. So how it works. In magnetic hard disk, this is nothing but collection of multiple n number of disks like this. So I'll have n number of disks. Each disk can occupy some spaces, some data it can store, each disk. And we have two sides, upper side and lower side. For each disk we have upper side, lower side, and both the sides can store some information. Now connected with one rotary. Fine. And this rotary can move your disk either clockwise or anti-clockwise. It can rotate like this or this. Fine. With the help of some disk driver. This disk driver will help you to rotate clockwise or anti-clockwise. Fine. Now suppose I want to access any data from your disk. It may be from the upper side or lower side. For that, I have a read-write header here. This read-write header can read or write any data from your disk. Fine. And this read-write header, for each disk I have two read-write headers. One is for top side and one is for lower side or down side. And we can move this read-write header forward or backward like this. It can move like this or this. Your disk can rotate like this or like this, so that I can access any one particular section of the disk by rotating and moving this on forward and backward. Fine. So this again, one thing you have to remember here, this read-write header are not exactly attached with the disk. There is a gap, thin gap is there. Through the thin gap, it can sense the data, read or write the data. I'll explain this. So I hope you understood how this magnetic hard disk looks like. Fine. Now each disk, if you see each disk, this is how it looks like. So I have, this is a disk, I have n number of tracks. There will be n number of tracks like this. Fine. And there will be n number of sectors also like this. So this is track 0, track 1, track 2, like this. You have n number of tracks, and we have sectors also. This is sector 0, sector 1, sector 2, sector 3, sector 4, sector 5. In track 0 I have 5 sectors, in track 1 I have 5 sectors, in track 2 5 sectors. So in each track I will have equal number of sectors. I hope you understood what is track and what is sector. Fine. Typically each sector can contain 512 kilobyte of data. Typically. Now suppose I have n number of disks like this. So for all the disks I will have n number of tracks, n number of sectors. So suppose these are the 3 disks I have in my magnetic hard disk, and for all these 3 disks, if I see I have track 0, track 0, track 0 in each of the disks. I have sector 0, sector 0, sector 0 I have. So this sector 0 from track 0 in the disk 0, sector 0 from the track 0 in disk 1, sector 0 from the track 0 disk 2, all these same location, same sectors are known as cylinder. Fine. So if I tell you how many cylinders I have, it depends how many sectors I have in each disk, right? So collection of same sectors from all the disks are known as cylinder. So I hope you understood this. Now let's see a good diagram. Same thing whatever I explained we have here, and this is how your read-write header looks like. As I told you, there is a thin gap, magnetic thin gap. Fine, it is not attached directly. If it is attached, then obviously you cannot rotate your disk, right? Now how it works? It works through some magnetizing current. It will generate some magnetizing current or magnetizing signals. Through that signals, your disk can sense the data. Your read-write header can sense the data through the signals. How the signals look like? This is some. So it will generate some signals like this. Now this is a responsibility to know what this signal means. What is this signals all about? For that we have some encoding techniques. The most important encoding techniques we use is phase encoding, and the same encoding technique is also known as Manchester encoding. So how it works? Suppose this is the signal you got. This is the signal you have generated or your read-write header generated. Now what does it mean? Using Manchester encoding we can decode it. How to decode it? We'll see from each pulse, from each clock cycle, I will see the midpoint. Only the midpoint. So if you see here, the midpoint is in lower side, so this is 0. So here the midpoint is in upper side 1. Here also upper side 1. Here also upper side 1. Here it's in lower side 0. So if I'm getting a signal like this, that means I got the data or the information called 01110. Understood that? So this is how it works. So this sector 0 track, sector and track I have already discussed. So I know this discussion was a very fast discussion. I discussed only the major points about virtual memory and the secondary storage. So that's all for this discussion or this lecture. Thank you for watching the video.